So today we're going to continue on with this probability unit. The second topic, of course, is theoretical probability. Here we go. So we're going to expand what we learned last class about experimental probability to a very, very similar concept called theoretical probability. It's hardly going to seem like anything new today, so this lesson should go pretty quick. But I'll just tell you right now, you might want to pause the video and try each question on your own as I go through this, and then watch for how I solved each question. Because again, this theoretical probability idea that we're going to cover today is very similar to the experimental probability that we covered yesterday. If you don't want to do that though, and you want to just absorb the information, you can do that. It's up to you really, no big deal. All right, so theoretical probability. I want you to recall from last class, we investigated something called experimental probability as being PA, that means the probability of event A, is the number of occurrences of event A divided by the total number of possible outcomes. So in other words, like let's say you did a bunch of trials. Let's say you did like 20 trials for something, and then you noticed that the thing you were looking for, event A, happened 9 times. Well, then, of course, your probability would be 9 out of 20, right? It's just the number of times you saw event A happen over the total number of possible outcomes or the total number of trials you tried in the whole experiment, right? Now, today we're going to deal with theoretical probability. This is calculated in pretty much the exact same way, but the only difference is that a trial has never actually been done. In other words, you're just looking at the theoretical outcomes. You're looking at how many times event A generally could happen out of the total number of times that you possibly have, or total number of outcomes you possibly have. This is way easier to understand with just like a bunch of examples. Probably the simplest example is imagine when you're flipping a coin. Now, when you're flipping a coin, it can either be heads or tails. There's only 2 different options, right? So if you counted heads as a win, then that would be your event A. If you did an experiment and you flipped the coin 10 times and you got heads 3 times, then you'd say P of heads, or probability of heads, is 3 out of 10, or in other words, 30%. Now, logically, however, because heads is only one of 2 options, the probability of heads should be 50%, or in other words, 1 out of 2. 1 possibility out of 2 total possibilities, heads or tails. So the logical conclusion that we got here, that is your theoretical probability. The theoretical probability when you flip a coin of getting heads is 1 out of 2, or in other words, 50%. Keep in mind the experimental probability that we covered last class is a little weird because it can change from one trial to the next. So if in this trial you flipped the coin 10 times, you got heads 3 out of those 10 times, maybe you did the trial again and you got heads 7 times, or 4 times, or 1 time, or not once at all, right? It could change from one trial to the next. It's all depending on luck, and that, of course, is impossible to perfectly predict, but theoretical probability is a good way of showing over time what the probability of either heads or tails, for instance, would be. Now let's do another example here. Again, if you want to pause this one and give it a try on your own, you can, or you can just watch me go through it. It's up to you. A deck of playing cards has 52 cards in it. Cards are organized into 4 different suits. Those suits are, of course, hearts, diamonds, clubs, and spades, in case you weren't aware, and also 2 colors, black and red. Now, hearts and diamonds are red, and clubs and spades are black, okay? So what is the theoretical probability? Again, no trial has actually been done here. We're just looking at our options and saying what we've got. What is the theoretical probability of drawing each card? Let's first start with a king of diamonds. Well, there is only 1 king of diamonds in a 52 card deck, right? King of diamonds is exclusive to just 1 card, right? There's 4 different kings. There's a king of hearts, a king of diamonds, a king of clubs, and a king of spades, but there is only 1 king of diamonds. So our theoretical probability would be written as 1 possibility out of the total number of possibilities when you draw a card. Well, there's 52 cards in the deck, so 1 out of 52. Remember that probability can be written as a fraction, or it can be written as a decimal, or it can be written as a percent. If you tried to write this as a decimal, you're going to get kind of a messy decimal, so I think writing it just as a fraction is probably the best way of representing it. So I will say my theoretical probability is 1 out of 52, and I'm going to leave it there because it didn't say how else to express it. Next one, a black jack. Okay, remember, jack is just a type of card, kind of like a king is a type of card. There's a jack in each suit. There's a jack of hearts, a jack of diamonds, a jack of clubs, and a jack of spades. But black, of course, are for clubs and spades. So what this is really saying, a black jack is either the jack of clubs or the jack of spades. So if you think about it that way, in a deck of cards, there are 2 black jacks. So in other words, we could say that this is 2 out of the total number of cards in the deck, which is 52. This is totally fine as an answer, but just generally speaking, just so you know, we often try to reduce our fraction to the lowest possible terms if possible. Well, this one, we can divide both the top and the bottom by 2. So I will do that. 2 divided by 2 is 1. 52 divided by 2 is 26. So 1 out of 26 is probably the best way of saying that theoretical probability. All right, the last question here is anything other than a spade. So remember, a spade is one of the 4 suits. In case you're not aware, the number of cards in each suit is actually 13. So 13 per suit. And in case you're wondering how I could find that, we know there's 52 cards in the whole deck, and there's 4 different suits. So 52 divided by 4 equals that 13. What I'm trying to say here is there's 13 cards in this deck that are spades, right? But we don't want them. We want anything other than a spade. So anything other than a spade. So hearts, diamonds, or clubs, that's what we're considering as our positive outcome. Well, let's think about it this way. There's 13 spades. How many cards are there of everything else? Well, you could find it by going 52 cards in the deck minus the spades, so minus 13. 52 minus 13, I believe, is 39. So there are 39 cards in a deck that are not a spade. So we could write that, therefore, as 39 over 52. Now, just off the top of my head, I'm not too sure if this simplifies. So let's just think about it real quick. 39 over 52, they both don't divide by 2, so I can't reduce it that way. They both, well, this one definitely divides by 3. This one, however, does not divide by 3. 52 doesn't get divided by 3. But I do know, actually, a really weird number that both of these numbers would divide by. It just kind of clicked into me. 13. Both of these numbers will divide by 13. And if you don't believe me, we could give it a try. 39 divided by 13 is actually going to be 3. And 52 divided by 13 shouldn't be a big surprise, because remember, there was 4 different suits, and we divided 52 by 4 to get 13. So if you went the other way around and said 52 divided by 13, you're actually going to get 4. So in other words, there is a 3 out of 4 chance of getting anything other than a spade. Putting it that way actually almost made it easier, because we could think of, instead of all 52 cards in the deck, you could have just thought of it as 4 different suits and said, well, there's 3 suits that aren't spades, so it's 3 out of 4. That would work as well, right? We just kind of overcomplicated it. But you know what? Whatever works for you. All right, next one. The picture shows a spinner. So imagine, like, this was just the best picture I could find, the one I wanted to use. Imagine like there's like a little thing here with an arrow, and it could spin around, okay? So the picture shows a spinner. Calculate the probability of each of the following outcomes. What's the probability of landing on the blue section? So any of these pieces right here. Well, by the looks of it, all of these pieces are all the same size. And that's pretty important, because if one of them was bigger than the other, then that would have a higher probability than the others. But fortunately, we don't have to worry about that. It was made a little easier for us. There are 3 different segments on here that are blue. So we're going to say there's 3 positive outcomes. And there's 8 sections in total. So we'll say that that's 3 out of 8. And that doesn't simplify down any further. So I would say we're done on that one, right? Now the next one, landing on a number that's a multiple of 3. That's an interesting one. Multiple of 3. Well, multiples of 3 would be 3, 6, 9, yada, yada, yada. But the highest number on here is 8. So really, we're just looking at either 3 or 6. So we're looking at 3 and 6 as being our successful outcomes. That's only 2 different blocks. So we'll say it's 2 out of 8. And 2 out of 8, that totally simplifies down. You can divide both of those by 2. That'll make it 1 out of 4. So there's a 1/4 chance of landing on a number that's a multiple of 3. Last one here, it's kind of like the one we had before with the spades, not landing on purple. So in other words, purple is not a successful outcome. Everything else, however, is. Well, there's 1, 2, 3, 4, 5, 6 that aren't purple. So we'll say that's 6 out of 8. And both of these numbers actually divide by 2, so we can simplify it down. And this is kind of a weird coincidence. Just like the spade one, the answer would be 3 out of 4. Right? So there's a 3 out of 4 chance of spinning the spinner here and not landing on purple. All right, next one. A standard 6-sided die is rolled. Calculate the probability of rolling an even number. Well, of course, a dice has 1, 2, 3, 4, 5, and 6 as its sides. Even numbers of that would be 2, 4, and 6. So you got 3 possible outcomes that are going to work. So we'll say it's 3 out of, well, there's 6 sides, so 3 out of 6 equals 1 out of 2, because you can divide both of those by 3. Clearly, 3 out of 6 is 1/2. So there's a 1 out of 2, or a 50% probability of rolling an even number on this one. Next one, not 1, 2, or 3. So in other words, what we're counting as successful is 4, 5, or 6. Okay, well, there's 3 things that are successful out of 6 options in total. Once again, it's 1 out of 2. Last one here is a bit tricky, and I'm not sure if you know very well what this is. A prime number. Prime numbers are numbers that are only divisible by themselves and 1. So I'll give you an example that's not on a dice. 13 is a prime number. 13 is a prime number because you can't divide it by any other number other than 1 and 13, right? So it only divides by 1 and itself. You could give it a try. If you tried dividing 13 by 2, you're going to get like 6.5. That's not a whole number, so it's not divisible by any other number, right? It's not divisible by 3, not by 4, not by 5, etc., right? So 13 is a prime number. Well, if we think about on a dice, of course, the numbers on a dice are 1, 2, 3, 4, 5, and 6. Let's test each one of these to figure out whether or not they're prime. Well, 1, the only thing you can divide 1 by is 1 and, of course, itself, which is 1. So 1 is a prime number. That's why. 2 can be divided by 1, of course, but it can also be divided by itself, but there's no other numbers that 2 can be divided by, so 2 is actually also a prime number. 3 has the same story going on for it. You can divide 3 by itself and by 1, but there's no other number you could divide 3 by, so 3 is also a prime number. But then we hit 4. 4, of course, can be divided by 1 like everything else can. 4 is also divisible by 4 because it's itself. But keep in mind, 4 can be divided by 2, right? 4 divided by 2 is 2. Since 4 can be divided by 2, it is not a prime number. Now we'll check 5. 5 can't be divided by anything other than itself or 1. So in other words, 5 is a prime number. And then 6, on the other hand, 6 is definitely not a prime number because 6 could be divided by 2, but 6 could also be divided by 3. So there's several numbers now that are actually able to divide 6. So 6 is not a prime number. So in other words, what we're counting as a successful number on this is 1, 2, 3, and 5. So there are 4 possibilities that are successful out of 6 possibilities in total. This can simplify down. You can divide both of these by 2. So the probability as a reduced fraction would be 2 out of 3. Okay, so here's some extra tips. Keep in mind, just because something has happened before or just before, doesn't mean you are any more or less likely to have something happen again. So there's going to be some questions you're going to encounter. They're going to try to slip you up on this by saying, oh, something just happened. What's the probability of it happening again? Well, just because something just happened doesn't mean that you're any more or less likely to have it happen again. So for example, and this is something a lot of people just don't understand. For example, if someone won the lottery, they got super lucky and they won the lottery one week, and then for whatever reason, the next week they decided to play it again, even though I guess they just weren't happy with the millions of dollars they just won. They decided to play the lottery again the next week. Their probability of winning in that next week would be the same as anyone else's. Like they would be just as likely to win the lottery that next week as anyone else would be. Like looking at where probabilities affect other probabilities is called conditional probability, and we don't deal with that in Math 30-3. There's a lot more things that you have to keep in mind when you do those ones. So just keep in mind any question that you're going to see is going to be something where it doesn't actually matter what happened before, right? Yeah, so just to clarify on this, conditional probability is a thing, okay? But it's just not going to be something we look at in this course. This intuitive idea of people winning the lottery twice in a row is a matter of how you word the probability situation, just to be a little bit more clear. If you have already won the lottery and then you play the lottery again, your probability of winning is the same as anyone else's. But if you reworded this question to say, what's the probability of someone winning the lottery 2 weeks in a row? Then that comes into conditional probability. And yes, then it's a much less likely situation, winning it twice in a row. But under the condition that you've already won the lottery, that doesn't affect your odds, or I mean your probability of winning the lottery again. Hopefully that makes sense. We'll look at a quick example. Again, like the examples you're going to see are going to be very similar to this. Suppose a couple had 2 daughters already. So they already had two girls. What is the probability that their third child will also be a girl? Well, there's only like, when you have a child, there's only 2 probabilities. It's either going to be a boy or a girl. So you have a girl being this, what we're going to call successful in this case, out of 2 probabilities. So it's a 1 out of 2, or in other words, 50%. Just because the couple already had 2 daughters doesn't mean that they're going to be guaranteed or whatever, or more likely to have a boy as their third child, right? Now, if you reworded this question and said a couple that doesn't have any kids is going to start having kids, what's the probability that they're going to have 3 daughters in a row? That's a different question. That gets a little bit more complicated. We won't deal with questions like that. Anyway, so enough rambling. To practice, I want you to do page 155 to 162, just any of the practice problems that are in there. As always, if you need any help, just reach out and let me know.